Good morning. How are you doing? I'm Mr. Ish. Thank you for joining me. I woke up here to a snow day, a very heavy snow overnight. So I decided to call out from work, and it seems like an ideal situation here to do a good math video, a good question, and make this moment even more momentous for you all. So I'll be switching gears now, and let me show you a little bit more of what we got going on here. We got snow over here and a lot of heavy snow right here on the trees. That's the view here from my living room, but momentarily we'll switch gears and I'll go to my board and then we can look at a good question and make this a little bit more meaningful. Thank you. Thank you for joining me. Now I have moved upstairs to my room where we will actually do this question. We have an interesting question here. We have a snowball that's thrown upward with a speed of 20 meters per second from a height 20 meters above the ground. We have to find the maximum height reached. We also have to find the time at the maximum height and the time at impact. These three things we have to find. You know, everything here is going to play either in one of two ways. You can do everything with regards to derivatives or antiderivatives, or you can do everything here with regards to integrals. A snowball being thrown upward with a speed of 20 meters per second from a height 20 meters above the ground. We have to find these three things. When a ball is thrown upwards, a snowball, it's counteracted against by the gravity. If you're looking here with regards to vectors, the ball being thrown upwards constantly, the velocity is decreasing as it's going up because the snowball has to eventually come down. Everything here, you can, with regards to acceleration, think of it as a minus, and then we can do a 9.8 meters per second square. That right there can be our vector representation for the acceleration. If you think about acceleration and you do its integral, you end up at the velocity function, and that's the way we can do it. We can just take this, we can integrate this specific function right here. It is a function. When you integrate it, you get minus 9.8 t plus c, but we know what c over here will indicate your constant of integration. It right here will indicate your initial velocity because it's thrown at a speed of 20, and that right there represents the equation, and we can identify it for you. The velocity function is minus 9.8 t plus 20. Now when you are doing it, you have to find the time at maximum height. When the snowball is at its maximum height, what do we know about the velocity? It will be equal to 0. Why? Because that's when the vector direction will change and it'll start coming down. The snowball will start coming down. You can take this exact same equation, minus 9.8 t plus 20, and equal it to 0 and solve for t. When you solve for t, it'll give you the time at the maximum height of that snowball. You have a 20 minus divided by 9.8 minus, you get 2.0408. 2.0408 seconds. And that's a figure we can save right here. Time at maximum, 2.0408 seconds, and we'll save it. Now that we've determined the velocity function, we can do the position function. I know the velocity function, I have it here in my head. So let me erase this and get to the next step. For the position function, I know the position function comes from the integral. Remember, I'm doing the integral approach here. The position function comes from the integral of your velocity function. If I know what my velocity function is, it's minus 9.8 t plus 20, and we're doing this. When you integrate this, you get a minus 9.8 t square over 2, which is a minus 4.9 t square. Remember, it's polynomial integration. Plus 20t plus, well, we can put a d over here. Our constant of integration here is d. We can represent d here by a numerical value 20 because the ball is being thrown, the snowball, from an initial height of 20. And that right there becomes my position function, utilizing the fact that the ball was initially thrown from a height 20 meters above the ground. We have to now find basically the time at impact, and we have to find the maximum height. We can find the time at impact. What do you know about the time at impact? Meaning the ball has hit the ground. With regards to the position, it should always then equal 0, because now your position will be represented by the numerical value 0 because the ball has hit the ground. You have here a quadratic equation. Everything here boils down in the end to a quadratic equation. You know, the quadratic equation will look something like this. You have a minus here, a downward facing parabola. You have a pretty large vertical stretch. You could have something very well like this. And I don't know what here the x-intercept is, and I'm not worrying too much about it, but in a very rough estimated manner, we could have something which looks like this. We won't here go into the negative sides, but it could very well look something like this. This right here, this x comma y, This x value here would be the time, and then the y value here is your meters or your position, the vertical height. At this specific point you have the maximum height and the time at that maximum height. At this specific point you have at the time at impact, and that's exactly what we're looking at right over here. We don't have to worry too much about graph because our approach here is just right. We'll still get to the right answer. Quadratic equation, quadratic formula, a, b, and c. We'll have here a minus 20 plus and minus b square minus 4ac. We'll have a 400 minus 4 times minus 4.9 times 20 all divided by 2 times minus 4.9. We have to basically aim for the answer which will be positive. You will disregard the negative answer and we will maintain the positive answer. Let's look at the root portion. We have a 4 times 4.9 times 20. That's a positive plus 400, and I'll square root it. When I square root I have a 28.14. This 28.14 can be viewed as a positive or a minus, but I'll keep the minus here because everything here in the end will divide by a minus anyways. I'll add to it a 20 and I'll divide it by what would have been a minus 9.8, but I'll write as a positive 9.8 because this minus here and the minus here cancel out, and we get over here 4.912. What does this 4.912 represent? It represents time, and we should put that here in seconds. 4.912 seconds is the time it takes for this snowball to hit the ground, the time at impact. So I need to save this value. I can erase this, you've seen the procedure. The time maximum was 2.0408 seconds, and the time at impact of the snowball to the ground is 4.912 seconds. Now what I need to do is basically answer the last question. Think back to the parabola I was showing you. At the peak, the vertex of that parabola, the downward facing parabola, we have the time at maximum and we have the maximum height represented by the y value. How do you get to that? You just take this same equation right over here and you plug in this time, the time at maximum. In all of these places of t, I'm plugging here t is equal to 2.0408 because the quadratic equation has not changed. The only thing that you're changing here is the input which will go in. So when you're doing here with the position function, you're putting here 2.0408 seconds, and that'll give you the maximum height. The maximum height will be that value plugged in here, and let's do it. We have here 2.0408, we'll square it, we multiply by 4.9 minus, that's this part right here. Then we'll add it to 20 times 2.0408, then we'll add that to this 20 here because it was 20 meters above the ground. We have here 40.408, and we can write it off, 40.408 meters. That's the maximum height reached at the time 2.0408 seconds, with the snowball hitting the ground at 4.912 seconds. Everything here done with regards to a logical integral approach. And that's all I wanted to present you. But keep in mind here before we tune out that this right here is again motion here in a linear straight line. Everything here is linear. Very well, the snowball was thrown from a certain height, it went up and then it went right down. The fact that it hit the ground and the fact that it started at a higher height, it's represented here, but everything here is straight line motion in one dimension, so it's not too hard. We have everything here represented. Thank you for watching. Have a nice day.